Greetings. We will continue our discussion on chaotic dynamical systems. We had a little bit of discussion on bifurcations in our previous class, and we started talking about chaos in general. We mentioned the terms attractors and also the strange attractor, and we will examine this in some further detail in today's class. Now, our consideration over here is the following. As we mentioned earlier, that if you have a system whose initial state is represented by this blue point, which represents the initial state of the system in a certain configuration space or phase space, or it is any initial condition of a set of parameters in which you are interested in it, and these parameters over a passage of time, let us say, evolve. This is the temporal evolution over a passage of time, and if we consider two initial conditions as we see in this lower figure, which are very close to each other, we expect that the evolution will proceed more or less along similar trajectories, and these are again are trajectories in whatever space we are talking about. It could be the configuration space or the phase space or some parameter space which represents the temporal evolution of the system. What often happens is that even if the initial conditions are very close to each other, the temporal evolution does not always go along paths which are close to each other, but they start diverging, and that essentially means that over a certain passage of time it will become impossible to predict what the system will evolve to after a sufficiently large time interval, and this is what leads to chaos, and this is what we mentioned in our previous class as the butterfly effect, that you can have a butterfly flutter in some part of the world, and then the flutter causes a sequence of events beginning with how the molecules of air knock the other adjacent molecules of the air, and how this effect cascades across from one point to the next to the next to the next, and travels not through just few angstroms or centimeters or meters or kilometers, but even thousands of kilometers, and it could actually cause a storm in some other part of the world. So, this is the butterfly effect that is often invoked to describe the sensitivity of the temporal evolution of a system to initial conditions. We studied in particular this map, this difference equation, which is a nonlinear equation. You see that there is a term which is quadratic in Pm, and it is a difference equation. The corresponding analog in differential equation did not lead to chaos as we saw, but in this map it does. And what it does is that depending on the actual value of the control parameter, which is this fecundity coefficient that we referred to in our previous discussion, this R, if it has got a value of 2.7, then if you sketch this Pn as a function of n, so you estimate its value from one generation to the next and plot it, then it rises rapidly, then there is a reversal, the slope changes, and you see these oscillations, but at some point these actually settle down to some value which we have considered as an attractor, because it settles down to that particular value, and there is really no chaos at all in this particular case. In order to examine the sensitivity of Pn to this control parameter, we considered a few other values. We considered R equal to 3, and we found that after a certain number of generations, Pn settles down to one of the two values. So, it is not unique, but you get one of the two values, either the one at the upper end of this curve or the one at the lower end, one of the two, and these two values actually alternate in what is called as period 2 oscillations, and you do not get any chaos, but the attractor is not a single value, it has got two values. For another value, if you keep increasing the value of r, if you go to 3.45 for example, now you find that the value of Pn that you get by solving this equation is not unique, but it has already gone through bifurcation and a bifurcation again. The result is that you get Pn to settle down to either one value or another or a third or a fourth, but then after the fourth one it comes back to the first, and then it is repetitive. So here you have period 4 oscillations. So here again the attractor is not a single value, it is one of the 4 values, but then the result of Pn does not go outside the set of these 4 values that we are talking about. However, if the control parameter exceeds 3.57, then there is absolutely no regularity and you simply cannot predict what Pn will turn out to be. And this is the bizarre behavior, because if it is just a little bit less than 3.57 like 3.55 for example, you are not going to see this behavior, you will get period 4 oscillations predictably, but if you exceed that, then you cannot make any prediction at all, and then the behavior becomes completely chaotic. So it is very sensitive to that value as to whether it is it is somewhat less than this 3.57 or somewhat greater than that. And this is what we have seen over here, that period doubling occurs at very specific values of the parameter r. So we have seen it happen here, then it happens here, then it happens here. Here again there is a period doubling, there is a bifurcation of the upper branch, there is a bifurcation of the lower branch again into this upper and this lower. So this is the upper branch of this one and this is the lower branch of this branch. So again there is this bifurcation which keeps taking place, and the first bifurcation takes place at the value of r equal to 3, the second bifurcation takes place at the value of r which is nearly 3.45 but not exact, it is 3.449 so on, and then the third bifurcation, so that instead of period 4 you will get period 8 oscillations, and this you will get at a value of r which is about 3.54, and then you get again at 3.56 you have this, but then if you exceed this then you run into the chaotic regime, then the behavior of the system, of the dynamical system being one which changes with over a passage of time, and the behavior of the dynamical system becomes completely chaotic. We also found out that if you take the ratios of these intervals, so this is essentially the interval between these vertical lines are drawn at those values of r at which the bifurcation takes place. So if you take adjacent segments and take the difference, so here in the numerator you have the difference between Rn plus 1 and Rn, and in the denominator you have a similar difference but corresponding to the next set, Rn plus 2 minus Rn plus 1. And if you take this ratio, then this ratio as n tends to infinity settles down to a constant. This is what is called as the Fuggin constant, and what it helps us is it tells us it is a scaling factor, and it tells us something about when you can expect chaos. So we also discussed the fact that chaotic does not mean random. Random would mean that if you have an initial value, then the result will be completely unpredictable, final state, if you have a given initial value. But what happens in chaos, that the same initial value will always present the same final state. So, that feature is not unpredictable. What is difficult is that the initial condition cannot be known with a huge amount of accuracy. You cannot know it with infinite accuracy, and therefore, if the initial condition is even slightly different, then the result will become completely unpredictable, and that is what leads to chaos. So, it is quite different from being random, and it is it has nothing to do with having a large number of parameters or anything like that. Here we are dealing with a single parameter whose initial value, if it is slightly lower than what would lead to chaos, you get regular behavior, but if it exceeds that value, then you get chaotic behavior. Also, this has nothing to do with the quantum theory, the quantum principle of uncertainty. So, this is a very exciting field, and it has got large number of consequences in various branches of science as well as engineering. These values need to be talked about with a high degree of precision to various places of decimals. So, I will let you find out what these values are from literature, or you can do some arithmetic on your own and calculate these values with your own programs and discover the exact values. So, this is how the picture looks like. This is a little bit of magnification of the previous figure, and it focuses on a certain region of the value of r. So, on the x axis from left to right, it is this value of r which is increasing from left to right. We already know that at r equal to 3 we had the first bifurcation, and then we had a number of bifurcations. So, we have one over here and another over here, but then we do see that there are certain regions. This one, for example, here you have 1, 2 and 3, and there seems to be a period 3 oscillation, and what is following period 3 oscillation is the bifurcation over here and over here and even over here. So, now we start looking at these details as to what is really going on. Now, these are certain isolated values of r, and a period 3 oscillation over here is obviously not chaos, because you can predict the attractor. The attractor is one of these 3 values. Okay, it is one of these 3 values, which means that the system will devolve to one of those 3, but you can predict that it will have to be one of these 3. So, it is not chaotic. So, there is a certain non-chaotic behavior for certain isolated values of r, and the cases of interest take place. We are looking at this particular region which is at r equal to, this is almost 3.82, this is 3.8, this is 3.9, and this is about 3.82, and here you see that at this value of r you have a range of parameters, not just a unique one, but from here up to here. Okay, so, r can be 3.82 and a little more than 3.82 and a little bit more than that as well, and you will continue to have period 3 oscillations. So, over a certain range of parameters of r, notice this word range, over a range of these parameters you have oscillations of period 3, and after this you have bifurcations over here. So, then you have period 6 oscillations, and then period 12 and period 24 and so on, and then you get chaos again. Okay. Now, this is a very famous theorem named after James York. This is called as York's theorem. What he found out is that period 3 implies chaos, that if you have a one dimensional system and if a regular cycle of period 3 occurs, then the system will display regular cycles of every other length as well as completely chaotic cycles. Now, this is what York found out, and this is known as the York Serum. This is a very famous line in chaos theory, that period 3 implies chaos. This is for one dimensional systems. Now, let us see, let us study this in some further detail. Let us examine what is this nonlinearity. Now, if you consider a differential equation like this, this is the differential equation for a simple harmonic oscillator, which is very familiar to all of you. Now, you have the same differential equation for a simple pendulum if you construct, right. Then you have g over L sine theta, you know what theta is, this is the angle which the which the pendulum would make with a vertical line if it is suspended and set into oscillations. So, if you take sine theta as it is, then of course you have a nonlinear term, because sine theta is an expansion in all powers of theta. But if you linearize it, if you take the lowest approximation to sine theta for theta tending to 0 for small oscillations, and the oscillations, when you talk about small oscillations, what you mean that they are small enough for you to consider sine theta to be nearly equal to theta. So, in the regime that you are willing to accept this approximation, then you have linearization, and the advantage of linear systems is that you can work with the principle of superposition. For a nonlinear system, of course you cannot do linear superposition. So, linear systems are easier to work with, and the reason is that it consists of various parts which can be dealt with independently, and then you can superpose their solutions the way you generate these Lissajous figures, for example. Okay. So, you can solve the problems independently, and then you can superpose the solutions linearly to get the solution to the full problem, but for a linear system you cannot do this. So, let us look at the simple harmonic oscillator, and now we are looking at the phase space diagram. So, the phase space consists of the position and the momentum, and if you plot p and x, what you get from this solution, this is essentially the equation to an ellipse in the phase space. And you do know that x and p will both change from time to time. So, there will be a temporal evolution of both x and p. X will oscillate from this extreme to this extreme and back. So, x will oscillate like this, p will change from this to this, up and down, right. But the description of the state of the system, which is represented by the point at the phase space, will always remain on this trajectory, which is a closed path, which is an ellipse, and the system will not ever get out of this ellipse if the equation, if the dynamics is governed by the simple harmonic linear oscillator. What this essentially means is that the attractor of this particular system is this ellipse. It is a closed orbit, and when it is a periodic orbit, this attractor is called as a limit cycle. Okay. So, a limit cycle is essentially this periodic orbit, and an attractor can also be a fixed point, but it can also be a periodic orbit, and in this case this orbit is the attractor, which is the limit cycle. Now, here is a temporal evolution of V and X of a simple harmonic oscillator. This is from Dan Russell's website at the Kettering University, and he has a nice diagram. You can generate this yourself if you like. All you are doing is solving the equation for a simple harmonic oscillator. You have the solutions, sinusoidal solutions, right, and the position is a sinusoidal solution, which is shown by this black curve. The velocity is also a sinusoidal solution shown by the red curve, right, and the phase space trajectory is this ellipse as we discussed just now. So, the attractor is a repetitive orbit, which is called as a limit cycle in the phase space. Now, we do know that a linear harmonic oscillator is a very ideal kind of situation, and for real oscillators it is very difficult to avoid damping. So, when you do have damping, how will it affect the phase space diagram? So let us look at that, and here is the picture of the damped oscillator. You know that the amplitude of both the position and the velocity will eventually diminish. Okay. So this is the damped oscillator, and if you plot the phase space trajectory, then it will be this path which will spiral inward and settle down to the center, right, and it essentially means that the attractor for this would be a point, it will be a steady state of no motion at all. The damped oscillator, because after a certain passage of time, after sufficiently long time, it will settle down to a single point. So the attractor can be a closed orbit as we saw in the previous case, it can also be a single point like a steady state. This is a fixed point in the phase space. So the attractor can have various forms, it does not have to be a closed orbit, it does not have to be a single point. In the case of period 2 oscillations, it is one of the 2 values. In the case of period 4 oscillations, it is one of the 4 values, right, and in that context we are not talking about a point in the phase space, but we are talking about what is it that the system can evolve to. Now that question is answered in all of these issues. So you can have attractors of various kinds, and if you plot the time series, which is the traditional time series, and you can plot the corresponding phase space trajectories, then in the case of damping, then you can have a steady state which is reached, which is a closed orbit, or else in certain cases you may have cyclic orbits depending on the details of the cyclic pattern. You may have period 3 oscillations, right, and this you could have a repetition of this pattern over and over again, no matter how many generations you examine this, or you may have a temporal series of this kind, and this really looks chaotic in a certain sense. But what is interesting is that if you plot the corresponding phase space trajectory, you do recognize chaos, nevertheless it stays within a certain domain, it does not exit this particular domain. So it is chaotic, but remains in a certain domain. So this is the case of a strange attractor. So I will explain this in some further detail now, but I hope you are beginning to see the difference between an attractor and a strange attractor. Okay. So these examples again are from Gleick's book. So the classic example of a strange attractor, or sometimes it is also called as a Lorenz attractor, because one of the best known examples of a strange attractor is the Lorenz attractor, and this was studied by Edward Lorenz in the context of certain system of equations which he considered in atmospheric science, and this was published in the Journal of Atmospheric Science in 1963. And here he considered a dynamical system described by a set of equations. Now these equations x, y and z, these are coupled differential equations, as you can see. This is equation for dx by dt, this is dy by dt, this is dz by dt, and let us not worry about what this x, y and z are. These are 3 physical parameters, it could be the temperature, for example, it could be pressure, it could be anything, right. So I am not going to get into those details. What I am talking about is that if you have 3 parameters, x is a function of t, y is a function of t, z is a function of t, these are all functions of time, and the temporal evolution of these parameters is coupled. So the differential equation, the rate equation for x, which is given by dx by dt, is dependent not only on the value of x but also on the value of y. Likewise the differential equation for y depends on x and also on y and also on z. Now in physics or in science in general, you will run into all kinds of situations in which you have to deal with maybe 2 or 3 or 4 or more parameters, and the rate equations for them are coupled. And then if you construct a parameter space, these being independent degrees of freedom, you can plot x along the x axis, y along the y axis, and z along the z axis, and they do not have to be the space of the space axis in the Cartesian frame of reference. These are just 3 physical parameters x, y and z, but being independent you plot them along 3 orthogonal axes, and that becomes the mathematical parameter space which describe the temporal evolution of the system. Now Lorenz attractor, you can solve this for different values of sigma, rho and beta. There are 3 additional parameters, sigma, rho and beta, and these are the classic examples which have been discussed very extensively in literature. So you will find these examples in chaos literature, in textbooks and so on. Let us look at the solutions for these parameters now. Now what happens is that if you plot x as a function of time, you get this kind of chaos, okay, you get a completely chaotic behavior. Now you plot x as a function of time along one axis, y as a function of time along another, and z as a function of time along the third, and at a given instant of time you now have a point in this 3-dimensional parameter space which describes the physical system, and how this point traverses in this 3-dimensional space is now what will describe the temporal evolution of the dynamical system. It does not have to be the phase space, it does not have to be the configuration space, it does not have to be the Euclidean space, right. It is a mathematical space generated by 3 degrees of freedom, namely x, y and z, where these are 3 physical parameters of interest. They could be temperature, they could be pressure, they could be density, they could be viscosity, they could be just about anything, they could be population in some case, right. In biology these parameters may involve populations, they may involve the birth rates, they may involve the death rates, they may involve a very complex situation in which you have 2 different species, or one eats on the other, and then there may be some survival mechanism. So this is the kind of example that we began discussing with when we discuss the biological rate equations, right. So you may have populations represented by x, y and z. These may be the populations of 3 different species or organisms, and how they evolve with time is what you are studying, subject to certain values of sigma, beta and rho in the differential equation, right. So this is the set of differential equation that we are dealing with, and these are the values of sigma, rho and beta for which we have plotted the temporal evolution of the dynamical system. And notice that it looks very chaotic, but what is interesting is that the solution always remains within this box, it is not getting out. Where it is in the box is unpredictable, that behavior is bizarre, that is extremely sensitive to the initial condition. If you change the initial condition you will get a similar pattern, but not this. As a matter of fact you will get a pattern which over extended time evolution will evolve into a completely different pattern. You will see this figure in one of our next slides, you will see that as well, and what you are seeing over here is that there is chaos, but the motion is in a certain space which nevertheless is confined within the box. So there is an attractor, but now you cannot describe this attractor as a steady state like a single point, or as one of the 2 alternative values as you have in a period 2 oscillation, or one of the possible 4 values as you have in a period 4 oscillation, or in damping you know that you have a steady state, right. But you do have an attractor, but you do not have any simple description for this. So this is called as a strange attractor. Now this solution, it does not converge to a steady state, but it does not diverge, it does not blow up to such an extent that the solution will go out of the box, it will remain in the box. So it does not completely diverge. So there is some kind of order amidst disorder, okay. So there is chaos, but there is some confinement of the state of the system over a passage of time. So this is what is meant by a strange attractor. Now let us ask this question as to how does this pattern respond to initial conditions. Okay, it is very sensitive to initial conditions. It does not, the solution does not diverge to infinity, it remains confined to a bounded region of space. These are the characteristics of a strange attractor, that the solution will be chaotic, nevertheless remain in the confines of a bounded region of the parameter space that is of interest, and this picture will tell you how it is sensitive to the initial conditions. Now just look at the central figure which has got these colors, okay. Now let me see if I can get this cursor over here, yes, here it is. So look at the central figure, it looks like a figure of 8 in a certain sense, and if you look at this, there are different colors, and what these different colors correspond to are they show temporal evolutions over period, over a passage of time for slightly different initial condition. And if you remember this, that if you have the initial conditions to be slightly different, then just after t equal to 0, after the initial state, right, the evolution goes together more or less, but then with passage of time over large time intervals, over large time durations, then the solutions diverge, and then the initial curves which were on top of each other, and they being top of each other, you see only one color inside, which is this yellow, but then you begin to see the other colors. There is another one over here, this red and a blue and so on. So they, you can really see that they have branched out. So initially it is possible to predict what the temporal evolution is, it goes more or less together, but then the branching has already taken place because the dynamics is sensitive, it is extremely sensitive to the initial condition, and the differences may not show up in the earliest of times, but over sufficiently large time then these differences show up, and then you start seeing these different colors. So what you see also on this are these additional figures which are the projection of this on this plane. So if this is your x axis and this is your z axis, then this figure over here is the projection of this figure on this plane. Likewise this is a figure on this bottom plane, and this is the projection of this figure on this side, okay. So if this is x axis, this is y, and this is z, then the corresponding planes are the zx planes, the xy planes, and the yz planes, and you see the projections of this on these planes. Now there is a remarkable sensitivity to initial conditions which is characteristic of chaos. Now let us ask this question, what is the dimension of the Lorenz attractor? Now we know what a Lorenz attractor is. A Lorenz attractor is a strange attractor, okay. Now what do you think is the dimensionality of this figure? Is it 3 or is it 2? It does look something like a 2-dimensional object, but a little bit warped, right. So in a certain sense it is like a 2-dimensional object, in a certain sense it is like a 3-dimensional object, and in some sense the dimensionality of this is somewhere between 2 and 3. And now we get into the discussion on fractal dimensions. because the dimension is now a fraction, it is a fractional dimension. So we will now talk about what fractals are. This is a fractal dimension, and to introduce the idea of fractal dimension, we first consider an equilateral triangle. Okay. What we do now is we take the middle of each side. So there are 3 sides, okay, and what is the middle of this side? To get the middle of this side, we must divide this side into 3 equal parts. So there will be one part over here, one in the middle and one at the bottom end, right. So likewise we can divide this side also into 3 equal parts, one on the left, one in the middle and one on the right. This side also can be divided into 3 equal parts, one over here, one in the middle and one at this end. So what we will do is at each middle of each side we raise another equilateral triangle. Now this figure is not great because this triangle looks not exactly like an equilateral triangle. So if you have a very precise vision, you might be able to notice that some of the angles are not exactly 60 degrees. So let us not get into those debates, okay. So that is not the idea over here. What we are talking about is the exact middle of each side, the exact 1/3, so that on each side of this exact middle 1/3 there is the remaining 1/3 on both sides, okay. So there are these 3 1/3s which will add up to one side, and we are talking about the exact 1/3 in the middle, and on this middle exact 1/3 we construct an exact equilateral triangle with the 3 sides being equal to each other, each angle being 60 degrees. Now that is the mathematical object that we are talking about, okay. What I have on this figure is not a mathematical object, it is some picture which I have inserted on the slide. So that is not a mathematical object, okay, it is a picture. What we are talking about is the exact mathematical equilateral triangle which is raised on the middle 1/3 of each side of the triangle. Now you have a triangle over here, okay. Now this also has got 3 sides. So one is the side on which this triangle is standing, right, that is the base, and on this one, on this side again you divide this into 3 parts, one at the top, one in the middle and one at the bottom, and on the middle you construct another equilateral triangle. Can you do that? Got it? Now again you have a triangle over here, this is the small one now, but this also has got a certain length, and you can divide this length into 3 parts, again construct the middle part, again look at the middle part, and on this middle part again raise an equilateral triangle. So there it goes, and you can do this on and on and on and on, right. What you will get is what is called as the Koch curve, okay. This is the result that you are going to get, okay, because you are going to do this not only on this side but also on this side and also on the bottom side, okay. You will do this on all the sides, it looks like snowflakes. This is called as the Koch curve. What we are doing is we are exploiting self similarity. We chose to implement a certain process. The process was to divide the triangle, the side of the triangle, into 3 parts, and on the middle raise an equilateral triangle. Then whatever triangle you get, look at its sides, and on the middle again raise an equilateral triangle. So here is a process, and we repeat this process, no stopping. The sides will get smaller and smaller, but you can always divide any infinitesimally small length into 3 equal parts. Okay. The idea of an infinity and the idea of an infinitesimal are amazing ideas in mathematics, and there is no stopping. You can do this endlessly, right. So what you notice is that the area of the figure that you generate is obviously less than the area of the circle which can be drawn around the original triangle, right. It has to fall in between that, so the area is certainly less than that. So this is the pattern that comes out of this process. This is the Koch curve. So the area of this is less than the area of the circle that we talked about. Okay, we have seen this in this picture. Here is this picture. So you obviously know that this area is finite, right. It will be some pi r square. So that is certainly a finite area. But if you now measure the perimeter of the Koch curve, how much will it be? Because every side you can keep dividing into small side and you keep measuring it, but then you have to take smaller and smaller scales to measure it. You obviously can't do it with a meter scale, you will need a smaller scale, and then you will need a scale which is smaller still, and then you will need a scale which is even smaller than that. But there will always be some additional length that you will have to add, and what you will get is a perimeter which is infinite. So you have got a finite area which is bounded by infinite perimeter. It is a very interesting object. So this was a Swedish mathematician who described this in 1904, more than 100 years ago, and then we asked this question, what is the dimensionality of the Koch curve, and just like the strange attractor, it seems to be more than 1 but less than 2, but we have not defined the fractal dimension as yet, so we are about to do it. It is more than a line, less than a plane. Normally when we talk about dimensions, we have in our minds the topological or Euclidean dimensions that we have common experience with, but there is another way of defining a dimension, and this idea was introduced by Felix Hausdorff, and this is sometimes called as the Hausdorff-Besikowicz dimension. Thanks to my Serbian collaborator Vojislav Radojevic, I can read these names. So this is Besikowicz. And we now introduce the definition of a fractal. It is a set for which the Hausdorff-Besikowicz dimension exceeds the topological dimension. So we have to define these quantities now. Okay. So this is the primary definition. So let us see how this works out. Now we do know that if you consider a point, it is a 0-dimensional object. If you consider a line, it is a 1-dimensional object. Okay. So let us begin with very simple ideas. A point which is a 0-dimensional object, a line which is a 1-dimensional object, a plane which is a 2-dimensional object, and typically these dimensions that we are talking about are the Euclidean topological dimensions, and in general you can write this as Rn space for the n-dimensional Euclidean space. It could be 1-dimensional, it could be 2-dimensional, it could be 3-dimensional, but we can also extend this idea for an n-dimensional Euclidean space, which is a mathematical space having similar properties. Okay. What we really mean by this, by the dimensionality of this space, is the number of real parameters which are needed to describe different points in that space. Okay, that is the idea which is at the back of our mind. When we talk about the dimensionality of a space, What we are really talking about is that you must specify those many number of real parameters. So in a Euclidean 3-dimensional space you must provide x, y and z, you need these 3 parameters, or if you are using spherical polar coordinates you will need the r, theta and phi, but you will need 3 parameters. Which 3 is a different matter, but you will need 3. Now this idea really breaks down, and there are Peano and Cantor's theorems. There is a one-to-one correspondence between R1 and R2, so I will not get into the mathematical details of this, but leave it as a self study idea for those of you who want to study this further. But we will come back to the basic idea of interest to us, which is this idea of a fractal dimension. So to do that, what we will do is we will begin with an object with a line which is a one-dimensional object. So we have a one-dimensional Euclidean dimension, we divide it into 2 parts, and when we do this we get 2 parts in 1 dimension. You can divide it into 3 parts, right, and then you get 3 equal parts of this kind, right. So there is this self similarity. The left part over here is completely identical to the right part. The middle part when n is equal to 3 is completely identical to the one on either sides. So this is the idea of self similarity that we are exploiting. So we are coming to the end of this class, and I am going to continue the discussion from this point, but please concentrate on this, that what we are doing is exploiting self similarity, that when you divide an object the way we constructed the Koch curve, okay, you started out with something, you generated 3 identical parts, and then you reproduced a triangle on the middle part, and then you did the same with the smaller triangle, but the smaller triangle also had 2 sides, the 3 sides, one the base on which the triangle was standing, and on the other sides again you constructed equilateral triangles on the middle part, and you started constructing this self similarity. And what we are now doing it is this with one line, that you take one line, divide it into 2 parts, or you can divide it into 3 parts, you can divide it into n parts, but when you divide it into a certain number of parts you get those many identical parts, and that is the self similarity that we are going to discuss in our next class, and that will lead us to the definition of what is called as a fractal dimension of an object. So if there is any question I will be happy to take, otherwise we continue from this point in the next class. Yes.
So can you go back to slide 71?
Which one?
71, earlier one.
Yeah,
right?
this one.
Now actually over here I could see triangles drawn in the other 2/3 of the part. In the other 2/3 part I could see triangles,
Yes,
triangles drawn.
right.
Now how do you determine the length of those triangles? Now we know that the bigger triangle is 1/3.
Well, the way you are going to measure length, and this point will become quite clear in the next class when we discuss this idea, because this was a very exciting question which was considered by Mandelbrot. And the question is that how do you measure the perimeter? How would you do it? Means you have got a certain arbitrary shaped object. The question that Mandelbrot addressed, which we will discuss in the next class, is what is the coast length of Great Britain? Now if you bring that map in front of you, or bring the map of India in front of you, right, and you have the Himalayas on the top, and then you have got you know the Bengal on one side and Gujarat and Maharashtra on the other, and then the V shape, right, and you want to measure the actual coast length. So you can't just take a meter scale or any scale which runs all the way from Trivandrum to Calcutta. That will not give you the correct length. You will have to take scales which are smaller to place them into the nooks and corners so that you get the exact coastline. You are going to have to do exactly the same thing over here. You will have to keep inserting smaller and smaller and smaller scales, which will keep adding to the length, which is how the length of the Koch curve becomes infinite, the parameter. That is exactly what makes the length infinite. But we will discuss this in some further detail in the next class.
The triangle in a plane.
Yes.
So how does the Koch curve finally it is in less than a plane?
Yeah, because finally when you talk about the perimeter itself, you are interested in the length. Now your idea of a length has got one dimensionality in your mind, a length which is the distance between this point and this point, okay, you stretch it out. Now if you take a thread to measure this length, then what you will do is run the thread over here, it will come out a little bit over here at this edge, and then you see that there is this shape of the bottle, so it will have to go inside and outside and inside and outside like this, okay. But then the length is going to be the stretch length of the thread, which is a one dimensional thing. So there is some notion of a one dimension which is contained in the idea of a perimeter. On the other hand, you are quite right, you started out with the plane, which is precisely what makes the dimension more than 1 and less than 2. But we will define it very rigorously in the next class. So thank you very much.